Welcome to our very last seminar speaker of the semester. Thanks again to Lockheed Martin for sponsoring this series. Today, I have the honor of introducing Dr. Sawyer Fuller. He is an assistant professor at the University of Washington in mechanical engineering. He got his BS and master's from MIT, and then his PhD from Caltech, where we overlapped for a few years. And then he went on to postdoc at Harvard and is now working on bio-inspired sensors, control systems, and mechanical design. So I will let him talk about his work. Thanks again.
Thank you, Mumu. So I direct this group in sunny Seattle, up in sunny Seattle. This is our group outing one day. Probably one of the coldest I've ever been. You don't expect it. It's not snowy. It's just raining and cold. At least that day. I direct a group called the Autonomous Insect Robotics Laboratory, and we are particularly interested in building robots the size of insects, and we take a lot of inspiration from insects. That's a key driver of what we do. And we build robots that look something like this guy. This is hovering, and it's a four-winged robot. Flavors Mother Nature never intended, but should have. Well, there are four-winged insects like dragonflies and bees, actually, but not in this configuration where all of the wings are splayed outward. This robot weighs a little more than a honeybee. It's 150 milligrams, 143 milligrams, and flaps its wings at 160 hertz, which is pretty comparable to what a honeybee flaps its wings at also. So why build insect robots? I'll start with that. And I think probably the vision that has captured me the strongest was suggested by this paper by Anita Flynn and Rodney Brooks, who is Brooks is the former director of the MIT AI lab, and he founded iRobot that makes the robot vacuums. So he had a crescendo of output back in the 80s that kind of cemented his place in the robotics pantheon. But one of them was this funny idea of exploring the universe using gnat robots. And so he envisioned that, well, if we can make our robots down the size of an insect, well, that makes it very cheap to send them to outer space at, I think, something like $10,000 a kilogram. If your robot is hundreds of milligrams, it's going to be very cheap to send a robot like that into space. And then they could perform this massively parallel exploration of the solar system, build moon bases even, crazy stuff like that. A little, but before we get there, that's a little bit farther off. So maybe a little closer to home, an application I like to think about that's going to probably come a little bit sooner, and that also plays to the strengths of very small robots, is finding chemical plumes. So this is something that is a sort of central theme of this talk, making a robot that could do a task like this. So the idea here would be you want a robot that can do something that many insects and even vultures do very well, which is that they follow plumes of odor through the air and then use that to find things like food or mates or I think bees maybe use odor as well to find flowers. They probably do, but there's a lot of things you can use odor to find. It's kind of the original sensory mode of biology, actually, was this chemical sensing. We don't really do that very much in robots, at least not yet. So you'd open up a suitcase of these guys, and they'd each be equipped with a chemical sensor. And then they do some rudimentary control. They'd avoid obstacles, move around. And then they would be programmed to cast across wind until they detected an odor of interest, and then follow the odor plume up until they, through some means, decided that they were at the source, whereupon they would land, emit a beacon, and then a human operator could then have some transponder, tricorder, whatever whatever you might call it, that could triangulate this beacon that's maybe a radio frequency beacon, something like that. So this plays to a lot of the strengths of robotic insects because it's something that probably requires the ability to fly into confined spaces. It is helped by the fact that you have, like, the more robots you have doing this task, the more comprehensive your search is going to be. So if you have many robots that are all cheap, that's probably going to be better at this task than one big robot. And it doesn't require complicated computation-heavy tasks like simultaneous localization and mapping. This is kind of a very reactive behavior, and very simple insects are able to perform this. So to do that entails a lot of engineering tasks to make a robot this small to do this. You have to figure out how to build them. You have to figure out how to actuate them. You have to put sensors on board. You have to put power systems on board. You have to do higher level control and navigation. And so this requires a whole, all the stack, all the things you might need for any robot really, but now they're going to be really small. Okay, so we have this great idea, but there's a lot of challenges. This hasn't been done yet. If you weren't sure, let me tell you, there are not yet autonomous insect robots. Okay, so we have this idea of why we want to do it, but so we're given this. The nice thing about it is it's a research problem. We don't know how to do this yet, and there's a lot of tasks. And the reason boils down to being that building this whole stack of components you need for an autonomous robot is not simply a matter of just shrinking them all from the size of a classic quadrotor like this, putting them down to the size of a fly. That's not going to work. And the reason is because we have scaling laws. Physics of scaling gets in the way. If you look at how small animals do what they do, and you compare that to how big animals do what they do, it's often quite different. Just to give an example, large birds glide. Very small birds like hummingbirds and small insects like flies and bees, they continually flap their wings because viscous drag is much higher as a fraction of the energy expended as you go to smaller and smaller scale. So you get a really bad glide ratio at small scale. So this physics of scaling manifests at a whole bunch of ways, not for everything from controls to sensing to computation. So just to give a few examples, that robot I showed you used flapping wings rather than spinning propellers, and the reason for that is that little spinny things just don't work very well. You get your viscous friction and your Coulomb friction as a fraction of the energy you expend. It gets much higher and higher because little motors have to spin very fast. That means a lot of viscous friction. And actually, the coils in electric motors, I don't mention that here, but little motors don't scale to small scale very well, also because they dissipate a lot of power in their coils because they get small cross-section area. So this suggests that we can't really use gliding flight, we can't really use propellers, so we're stuck, we probably want to use flapping wings instead. On the sensing, so we can go down. Sensing, global positioning probably is not a usable technology for positioning for an insect-sized robot because it's just not precise enough. We get maybe 10 meters of precision and it's fully denied indoors. Neither of these are useful then. This is a very big problem if you want to do something like fly through a doorway. We also probably have to do non-emissive sensing. Self-driving cars, they use these scanning laser rangefinders, but they use a lot of power. That's okay for a car, which is already using a lot of power because it's multiple tons. At an insect scale, we probably don't want to use emissive sensors. Let's see, what else? And control, we're kind of stuck between a rock and a hard place. It turns out as you go smaller, the rotational dynamics speed up, and the computation you have available to do control computations to compensate for these fast dynamics get worse and worse because you have less and less computation power because you can carry a much smaller battery. So you have this kind of rock in a hard place, faster dynamics and slower computation. You've got to figure out a way to do that. So small is different. As you start getting about the size of an insect, a lot of things start changing, and you have to throw away a lot of the techniques that have worked well for larger scale robots and flying things and develop new ones. Good news is that we know it's possible because we have these little organisms called flies, and they're both able to do it, and they're also able to do it really well. This fly is showing off as it manages to land on a chunk of lettuce. You can see it's almost flipping itself upside down at one point as it does these body saccades, and and you can also see that in between the saccades, it's under pretty good control because you can see its body is rotating relative to its head. It's keeping its head still to help it sense its location. So what this fly is doing is at the forefront of a lot of fields of engineering. It's got steady flow and the flapping wings. It's using minimal computation, low power computation, super aggressive dynamic controls, and all of this is done using resources that are totally on board. So we'd like to be able to do that in a synthetic system. So yeah, what really got me into this was I had the honor of being a part of what I would say is a nice breakthrough when, as a postdoctoral scholar in Rob Wood's group, we figured out how to make one of these little robots. This one is about the same size as that earlier one I showed you. We figured out how to do controlled flight. And so we got that working. That was kind of a mechanical proof that at least the fabrication and the actuation was well underway. But what you didn't see in that video is that there was a nice little fly robot flying there, and it's about a couple centimeters across. You didn't see that there's a whole bank of stuff behind supporting that. It had external cameras tracking the motion. It had a little wire going up to it to provide power and control signals. And the computer was a bank of literally 3 computers sitting under a desk to do the computations. So the rest of my talk is going to be focusing on the sort of manifest future of this. How can we go from this robot that required a rack full of equipment and turn it into an autonomous robot that can work anywhere rather than just in a very specific laboratory setting? So the things I'll talk about are things we've been working on in terms of building a better version of a robot fly, putting sensors on board, putting computers on board, and putting power on board. And those will all be needed to make this fly. So, okay. I'll start with how to build these guys. So Brooks and Flynn imagined initially that these robots would be built using technologies derived from semiconductor microchip manufacturing, so-called MEMS. They imagined you just build the whole flying robot on a single chunk of silicon. Since then, there have been a number of developments of larger robots made using what I would call, more classical fabrication techniques, nuts and bolts, 3D printing. It's not so classic, but it's generally better suited to larger things, casting, milling, these sorts of things. And they've given rise to these robots that have gotten down to about 1 gram in size, down to about 1 gram. These are 3 and 20 grams, this sort of size. And then, of course, semiconductor manufacturing, it closes this other size range down to a micron up to maybe a few millimeters parts. But the downside of using semiconductor MEMS fabrication, there's a little unhappy face on the gnat there, is it tends to take a long time to build stuff out of silicon. And that has really meant that that's really limited the progress on building flapping wing robots or little robots out of silicon. But if you're willing to go a little bit larger to this range of 1 to 20 millimeters, something like that, then some new fab tools open up that really have made the difference. And in particular, that tool is this diode pump solid state laser, ultraviolet laser machining. And here is a video of a laser we have in my lab that cutting out parts out of a piece of unidirectional prepreg carbon fiber. It takes just about a minute to cut through a sheet of carbon fiber. So you have this manufacturing process that goes very fast, and it's just a little bit bigger than silicon. The spot size is about 20 microns. It can cut through maybe 200 or 300 micron thick material, and it can do so, and it can cut through almost anything: ceramics, plastics, almost anything. Unlike what I would call a classic CO2 laser, which cuts wood and paper and plastics, but at a much larger. It basically heats the material to cut. This is a UV wavelength, 355 nanometer. So it's I'm not a chemist, but I think my understanding is it's not using heat to cut things. It's using it's chemically breaking the bonds through chemistry, using a much shorter, more powerful wavelength. So we can cut almost anything, and we can cut it in just a few minutes. So this allows an iteration time of just a few days of building our robots. We can build an insect robot in about a day, and we can iterate the design, build a new one a day or two later. So in addition to do that, we have this fabrication process. It's called Smart Composite Microstructures. Smart Composite Manufacturing. I forget what the M stands for, something like SCM. Anyway, it boils down to we cut up a series of sheets using the laser, and we pin align them. It gives us a precision repeatable of about a micron. We put that series of sheets together in a hot press, and a couple of these sheets are, this is a sheet adhesive, an acrylic sheet adhesive. Under heat and pressure, bond them together, put it back in the laser, cut a shape out, and then we get this laminate that looks like this. And then we fold that into shape using origami. So origami-inspired techniques. So it's sort of like a technique for building 3D structures at insect scale that gives us the ability to use very high-performance materials like carbon fiber, titanium, aluminum, almost anything. So that's been kind of instrumental in building insect-sized robots. The other part of the story is a suitable actuator, and what we've been focusing on is using piezo actuators. Here is how we use a piezo bimorph, which is two stacked pieces of piezo on top of each other to be the actuator. So the idea with a piezo is it's a material that if you apply an electric field, as shown by these little electric field lines, it shrinks in the other two directions. And if you alternately charge one or the other of these two sides, it does this oscillation, a tip motion that's pretty small. And then if you plug that into a laser fabricated mechanical system like this, it will amplify that tiny motion, geometrically amplify that tiny motion into a very large wing motion of about 90 to 100 degrees. Let's see. So this is what it looks like. This is what these piezo actuators look like on our flies. And then that is used to drive a wing. So we drive the sweep angle of the wing through the piezo, and then the angle of attack is allowed to rotate passively on a flexure, a compliant flexure. So as you push the wing, it naturally undergoes this wing kinematics that looks very much like what actual flies and bees do. And so the heritage of this robot design starts after Brooks and Flynn. Ron Fearing at Berkeley got a large grant to actually build one of these guys. And he recognized early on that new actuators that aren't electric motors were the right way to go. And so after a few years, they had started building ones out of metal that were too heavy, and they could flap their wings, but not very well. A few years later, they started switching to carbon fiber that got them better strength-to-weight ratio. And they could flap their wings at high frequency, but they still hadn't quite got lift to weight greater than 1. Then a few years later, my postdoctoral advisor, Rob Wood, figured out how to get lift greater than weight by vastly simplifying the mechanism and allowing the angle of attack to rotate passively. So we had many fewer actuators and made it much lighter. And then I was a part of making it fly controlled. And then a big step, I thought, was something we did at UW, which was the first robot to take off without a wire. We cut the wire for the first time by integrating the power system on board. So I'll talk about that some more. Okay. So, all right, things we've done to improve the design. So one of the problems we had was we had too many parts in the Robobee. I think it's something like 21 parts here. And if you've ever assembled tiny things with tweezers under a microscope, maybe if anybody's here has used surface mount components, if you soldered tiny surface mount components on an electric board, if you hold that with tweezers and do something wrong, that little part is just going to shoot into Neverland. It just shoots across the room and you'll never find it again. So here we have 21 parts like that. So what we've done at UW is kind of rethink the design, make it all these parts, or a lot of those parts, are now made from a single laminate sheet. So we make this flat sheet, fold it into shape, and this cuts drastically down the number of parts that a whole fly needs. We have a couple more layers, but much fewer parts, so I think that's a net win. The other thing we did with this design is we took the Robobee design, which, oops, that's the wrong order. We redesigned it, changed the direction of the piezos, and lowered the center of gravity a lot. This gives us some nice capabilities, one of which is that it makes it much easier to land on surfaces. It doesn't tend to topple over. And we also found that we can actually do multimodal locomotion by, it turns out if you flap the wings, you can actually make it move along the ground too. So now just using our wings, we can ambulate on the ground as well as the air, as well as fly. Here it is steering itself. And now we have a robot that can go under your doorway as well. We've kind of made an end run around this challenge of how do you grab a doorknob and open it? Just go under the door. So solve that problem.
If you have carpet?
You would have to, good question. The question is, what if you had carpet? We haven't tried doing it on carpet yet. I think you could still do it. You'd probably have to do lots of little hops, my guess. You'd probably hop and control yourself forward a little. Yeah. Good question, though. Yeah. Yeah, that was done on a flat surface. We, unless you think otherwise, it can fly as well. So that's 2 wings. I've been playing around with adding a few extra wings, which I showed a video of this earlier. Here's a 4-winger guy, and the way this works is on the top left is the nominal state. All 4 wings are flapping with equal magnitude. And if you've ever worked with a quadrotor, this probably looks very familiar. Same principle applies. If you want to do a roll torque, apply a roll torque, this guy, you just flap this wing with a larger amplitude than this wing, and the robot will tend to roll this way. This wing has more lift than this wing. So you roll. Same story for pitch over here, and you can yaw by flapping the wing faster in one direction than the other, applying more drag in one direction than the other. So one of the things about the Robobee, which is not often talked about, but you can actually see in this video, is the Robobee can't actuate around yaw, which is to say it can't steer around yaw. And the reasons are kind of complicated, but it boils down to the fact that the ability you have to apply a thrust, let's see, a yaw torque, a torque around a vertical axis, is limited by the fact that the angle of attack of the wing is allowed to rotate passively. And if the wings are really close together like this, the effect of the wire tether overcomes any ability of the robot to steer. So we had to spend a lot of energy building a controller that did not care what the orientation of the robot was. And you can see it's rotating all over the place as it moves around in response to this wire tether. So it'd be really nice to have that ability to steer, because then you could maybe aim a sensor, or you could aim your feet if you wanted to land, something like that. So the ability to steer a robot was something that's missing from this design. In this case, it's, well, probably a combination of air currents in the room and just that wire tether. The wire, as it moves around, the wire tether is pulling the robot around. So you can see it's making a large rotation.
I think that if it was the tether, there'd be stored energy in the twist in the tether, and it would, sort of...
You can see it kind of moves back after it gets to that extreme. Yeah. The other thing that, in practice, what happens is often the wire tether is a combination of twists and bends, and it'll suddenly twist out, and then your whole robot will just flip around, just kind of willy-nilly.
If you got rid of the tether,
it would be easier.
Slightly different speeds.
Yeah, if you got rid of the tether. Yeah. Yeah. I still think you want decent actuation authority around the yaw axis. But I think if you didn't have the tether, I think you'd probably be able to steer this direction you wanted. But for the interim, we wanted to be able to steer it despite the tether. So what this design gives us is it moves the wings much farther out from the center, and that gives you a much larger moment arm. And then through a number of videos, I showed that it was possible to steer this robot consistently in the direction that I commanded. So here's a right turn and there's a left turn. So now we can control heading. And here it is hovering. I think I showed you this video earlier. And it hovers too. Another thing you get with more wings is more payload. That's important if you want to carry sensors on board. So here it is lifting 2 toothpicks and a ball of solder, 260 milligrams. Just barely, but it's enough to prove it. Okay. Other improvements. Taking more inspiration from biology, and in particular lizards. They use their tails sometimes to maneuver their bodies in free flight. And so we thought, well, we have these piezo units that can actuate wings. What if we stuck a tail on instead of a wing? So here is a kind of a prototype of that. What we did was we built, so this kind of weird device has 3 actuators on it, and it's hanging from a tiny thin Kevlar filament. And what we did was we told it, and then we attached this. This is here, I'll just show you the video. So this is a tail. So we actuate it one direction, and we say turn the other direction as fast as we can. And what we see is that, well, the piezos are really springy, and that's good for flapping wings because it's a resonant system, but it's bad for something like this, where you want to move something fast, you excite this resonance, and now your robot is just wiggling like this. Previous tail-actuated robots have by and large used electric motors, so this was kind of a problem we encountered by using piezos instead of electric motors. So we developed this feedforward controller that estimated the resonance and supplied it a command that did not excite that resonant mode. So here's the springy version. Boing. And now we don't excite the mode at all. Pretty cool. So fast actuation with a springy actuator unit. And then we did some very preliminary work in free flight. There you can see the tail pitches. And after the robot has taken off, the tail does a quick move, and then by shifting the weight, now the robot starts to pitch back very fast. So we actually have two actuation pieces there. We're moving the tail, and that's pitching the robot a little bit, and then that in this flight, that changed the center of mass of the vehicle, and that caused a longer term pitch torque. So we're hoping this will turn into a way to make these guys really, really maneuverable. Another challenge is doing onboard power, and the big guy there is these piezos require high voltage, on the order of 200 to 300 volts. And what you need to make a robot that can fly is some ability to take a typical voltage that you get from a battery or from a photovoltaic, which is going to be just a small number of volts, and bump that up to this 200 or 300 volts in a circuit that fits within the size, weight, and power constraints of an insect-sized robot. So that's to say a power system that weighs less than a toothpick. So how do you do that? Well, we just built a really tiny boost converter, and we powered it with a laser. We avoided a battery because nobody yet builds a high drain battery that's this scale, so we're avoiding using a battery. So here's our robot fly being hit with a laser. Nice picture from our from our photo crew at UW. And with that laser, we built a ultra miniaturized boost converter on flex circuit. You can see here is a little tiny coil here, and a few transistors. And this circuit doesn't have it, but we also put the first brain on a robot fly. It lives in this spot there to control the whole thing. And that steps, using this clever coil, switching on and off quickly, it steps up the voltage up to what we need for piezos. And then here's a video we made for that. So we shoot laser to this photovoltaic cell. There's a microcontroller. Our first flight, we hadn't trimmed it, so it took off but kind of tilted. And then the next one, we trimmed it so that it flew more or less vertically here. And here it is in slow motion. And the flight is very short because the beam is fairly small. So as soon as it takes off, the photovoltaic moves out of the view of the laser. So that's yeah. So where we're going with that is the next step is to kind of steer the laser beam. So that's one piece of puzzle, one possible solution to the power problem. Just to give a taste of where we're going, I think we can also power these with Wi-Fi or cell phone signals. Those are very minute power sources, but you can actually collect power from these RF signals, and they're just very weak, probably too weak to power a large quadrotor drone, but maybe enough to power a little robot like this occasionally. Like you sit there and charge for an hour, and then you take off and fly for a few seconds, and then you do that. Okay, sensor autonomy. I want to talk a little bit about just getting started in this area. We're working on baby steps here. But what we want to do eventually is something like this. This is a larger quadrotor, and it's only using vision to fly here. Well, vision and it's not using GPS, let's say. And it's not using laser rangefinders. And it's able to do some pretty cool stuff, avoid trees, and also fly into this doorway there. And because we don't have GPS, we're probably going to need to do something like this to fly our robot fly. Here it's lining up for the door. Okay, finally found it. Just barely. Ooh, just made it. There it goes. So we'd like to be able to do something like that. Oh, don't run into the wall. We're going to do something like that but at an insect-sized robot. And the challenge here is this was done on a 2-kilogram, that's the helicopter that did it, and a computer that ran on 10 watts. But we're going to have maybe 10 milliwatts is our computation budget, because the whole fly uses maybe 100 milliwatts. So we have this challenge of doing visual flight control in a much smaller package. Here, maybe 1,000 times less compute power available, 1,000 times fewer pixels. That was a megapixel camera, and much less weight. So we're working on it. This is some work we did with Jeff Barrows here, which is he's local in Virginia, and he builds these tiny camera chips for a company called Sentai. And he gave us one of his chips, and we made a little pinhole camera, and then ran a neural network and programmed it to like flowers and dislike butterflies. So we run the neural network, and then the neural network actually we showed that we should be able to do this on a microcontroller on board at much faster than this, but we just did it slow because it was a demo. So we're taking baby steps, and hopefully some architecture like this with neural networks could be used to do things like detect the plume source either visually or detect a landing site, that sort of thing. And lastly, plume source localization. So how do we make our robot actually follow the plume? So the first thing to know about plume following is that turbulent flow, or most of the atmospheric flow we encounter in our daily lives is turbulent. Indoor airflow and outdoor airflow. And what that means in practice is that transport is carried out primarily by convection rather than diffusion. And so what that means as far as plume following is that you don't get nice gradients of chemical in your environment to follow. You get this patchy pattern that you can see in this plume of smoke from a cigarette. You get kind of these filaments of flow that are either on or off. And so insects know this, and what they do as a result is they don't tend to follow gradients to find plume sources. They do this this so-called cast and surge strategy that responds more to instantaneous characteristics of the plume flow. If a filament is encountered, cast upwind. If the plume is lost, if no filaments have been encountered for a while, start casting back and forth in larger and larger casts until the plume is detected again, and then surge upwind again. This is how a male moth of Bombyx mori, I think, looks for females. So that's the kind of probably how we're going to want to do this in robots. But the current state of the art is pretty far from that. And the reason is a lot of it is that the sensors that are kind of small enough to go on a flying robot are very slow. Here's a flying robot. It's about a meter across. I guess you can't see it in this picture, but it's flying in this open area. It's using GPS to track itself. And here's a tank of methane gas and a fan, so it gets a nice strong plume. And then it pauses at a location for 20 seconds to detect whether it's in the threshold inside the plume or not. So it's a very slow process, and it's sort of doing a pseudo cast and surge where it just integrates over a certain amount of time and then decides whether it's inside the plume or not. But we're going to need to make it go a lot faster than this and in more varied, complicated conditions like this, because this took basically a full battery charge to do this simple outdoor plume following. But we're going to want to be able to do it in indoor cluttered environments, that sort of thing. So what do we need to get there? And what I claim is that we need, first and foremost, a faster sensor. We also need to be able to do so without GPS, so we can go indoors, for example. We're eventually going to need to be able to avoid obstacles, and then we also probably need to do chemical discrimination, which is also tricky. And so I'm going to tell you about our steps toward that. We have some we don't have a chemical discrimination yet, but we have a path there, I think. But in the meantime, we've kind of got some of these things. And the approach we're taking, and this is with a collaborator, Tom Daniel, who's a biologist who primarily studies moths at UW, is we use the antenna of a moth. And so this is electroantennogram. Here's the moth. Put it here. Put a high gain electrophysiological amplifier there, and detect spikes from the neurons in the moth, receptor neurons. And then put this on a Crazy Fly, which is a commercial platform that can operate. They give open source software that allows it to operate indoors fully autonomously by using a downward facing camera and a gyroscope and a time of flight laser rangefinder that can measure its altitude. Let's see. And the kind of the big story is we have a really fast sensor here. This is passing a sensor, a plume of I think of an odor from a flower over the helicopter. It's sending this signal over Wi-Fi to the computer, but what you can see is those pulses are really narrow, much less than a second, rather than the kind of 20-second refractory time that these metal oxide semiconductor sensors need. So that's part one. The next part is making this fly autonomously. And here it is in a fan, and attached to the fan is this same chemical plume, and so it's detecting this plume and moving toward the plume. And we're using, so the other kind of great thing is that we turn the coordinate system into a wind-centered coordinate system. So the only thing that matters if you're plume following is the location of the source of the plume in wind-centered coordinates. So you just need to think about casting crosswind and going upwind. So if you always are facing into the wind, which these wind vanes do, then you only have to find two numbers, which is how far laterally you are and how far upwind you need to go. And so you cast laterally and then you move upwind. And these are all very easy things to do using this downward-facing camera to localize yourself. So there's no GPS. This is indoors, and it's following this plume. And then this is what it looks like actually doing plume casting. Sorry, we don't have a video of it, but it's doing cast and surge. On the right is what it does if there's no plume. It just casts back and forth. And in the middle, this is what it does when it detects a plume. It surges upwind, so it casts and then surges. And yeah, so we have a few trials where that worked. And the future there is going to be that the moth is not one of the classic genetic organisms, but these days we have CRISPR technology, and apparently that is something that can be applied to moths. And so we're hoping that a future part of this will be using genetically modified moths to make them very receptive to specific chemicals of interest, like an explosive or methane or something like that, and no other chemicals of interest. And then now we have this biological hybrid sensor that's much faster and more specific than could be possible with man-made sensors. Okay. So just to summarize, so I told you about using flying insect robotics, and I talked to you about how I think a good application that really plays to their strengths is finding gas leaks or finding sources of plumes, because it doesn't require a lot of computation and it is compatible with tiny sensors, maybe moth sensors. And this could be used for things like explosives, finding gas leaks, wildfires, and maybe exploration, space exploration down the road. And then we get a lot of nice research problems that come with the challenge of miniaturization, everything from how you build them to how do you control them. And so I told you about some improvements for using this basic fabrication design technique, using laser-based fabrication and piezo folding, laser-based fabrication and piezo actuation. And then added some new capabilities like landing, walking, and steering, and dynamic aggressive maneuvers. Starting to look at laser power sources like a laser, and we're looking at how to improve the sensing world by using a moth antenna. So this is the kind of the humble the modest proposal for how one node in possibly a swarm of these guys might look in the future. It's going to have this moth sensor for smelling things. It'll have a very low resolution camera for kind of navigating the world. Maybe it'll use optic flow to kind of a coarse but efficient version of optic flow that takes very little computation. Maybe we'll use wind sensing to help stabilize the coarse optic flow measurement we use. And yeah, and it'll have this chemical sensor on the top. And so this is going to be, we're going to hopefully deploy thousands of these and do some cool stuff with them. Okay. With that, thanks to the lab, Autonomous Insect Robotics Lab. Thanks to my funding sources and collaborators, and thanks for listening. Hit me with questions.
Use the CRISPR to modify moths to seek out the chemical sources. Why not just put a sensor on a moth instead of building a robot?
So why not just why not use the moth? I think there are cases where you might want to just use the moth. People have trained bees to find landmines. So we know that they can smell the smell from landmines. The way they've done that is they train the bees to associate landmines with the explosive with food, and so the bees tend to congregate there, and then they use a laser to find where the bees are. I would just say it's still not going to be as consistent as I think it would be possible to do with a robot. So that's I think ultimately we're going to want to have robots that we have more control over. But in the meantime, I think using fully biological systems has a place, and I'm not so full of hubris that I'm sure that robots are better. It might be that biology is better. It might be that we can just train them. We'll see. I guess I think we should try both of those approaches, and we'll find out which one wins. People have also done things like put backpacks on beetles and controlled them with a joystick, but that is also very much a work in progress, and it's a hard thing to do as well. So that would be another approach that would give us a little bit of control. Yeah, good question. Thanks. Yeah.
How are you keeping track of where your insect robots are, like once they're out in the world?
How are we going to keep track of them? They will have to keep track of themselves. Or one answer to your question is they're going to be disposable, and we're just going to let them go, and they'll disperse, and if any of them finds the source of a plume, it'll start emitting a beacon, and we'll be very interested in that one, and we won't care about the rest. It's also possible, it might be better if they came back, if they, we're going to run out of power, or after a certain amount of time or something. That's a good question. How would we get them back? One way is if you can use what this helicopter does, which has this sensor platform that I think we're going to want, is it can basically integrate by looking at the kind of speed of the optic flow underneath it. It can basically tell how far it's gone, and so it can retrace its steps. It'll be subject to a little bit of drift. But as long as you get close, that's probably all you need. And so that's probably the other half of the answer, is that we will expect them to, at least to some extent, know where they are and be able to retrace their steps and go back. Good question. Yeah.
Could you tell us a little more about the fabrication of the actuators themselves, and also how you anticipate doing like the aggressive maneuvers and incorporating other onboard sensors?
Okay, so how do we make, so the actuators are, the way we make the actuators is they're piezo sheets, and we score the surface of the piezo with our laser, and then we carefully cleave it at those scored surfaces to give us these trapezoidal shapes, and then we bond them to a carbon fiber layer in the middle that serves as something that makes it a little bit more rigid and sturdy, and tunes the stiffness to the stiffness we want for our resonant flapping wing system. Does that answer your question about the piezos? I'm happy to, I can give you a reference for our approach afterward if you want a paper about it. I can definitely send that to you, or just email me about it. Your other question was, how are we integrating sensors, and what sensors are we looking at?
I guess I'm just curious about like what type of like flapping controller you're using and how you might use like other inertial sensors to sort of control different maneuvers.
Aggressive maneuvers and sensors. So basically, to do that wireless flight, the microcontroller on board has to generate a sinusoid signal to drive the piezo actuators. That's and that one has this 200-volt amplitude. And the way it does that is basically lots of pulses charging from a capacitor either at 200 volts or shorting it to ground. And by the pulse frequency, you can use that to basically generate a kind of a bumpy sinusoid. And so those pulses happen something like 200 kilohertz, quite fast. So that's how we generate the sinusoid, and then we modulate those, maybe flap one wing harder than the other to do roll maneuvers or pitch maneuvers. And that gives us we have a lot of control authority with these flapping wings. And because of scaling, as you go smaller, you can go faster and faster. So we can actually maneuver very fast. We haven't yet gone faster than the fastest quadrotor I've seen, but I think that's only because we haven't tried. And we probably should do that and write a paper about it, but we just haven't done it yet. And then what we're going to need on board to kind of be able to compensate for that is, I think I don't have it drawn here, but there's going to be a gyroscope here too. And that in combination with optic flow and vision is going to give us our attitude stability. And gyroscopes, commercial gyroscopes are pretty small and good enough. We've been able to put one of them on this robot, and it's enough to give it attitude stability, despite the very vibrational environment of the flapping wings, because it's 200 hertz of doing this, and so it's like I measured it with the accelerometer. It's like a 5G acceleration, which is pretty good that this gyro still gives you good numbers despite that. It matched very well with the motion capture data. Yeah.
So how do you model these robots for the purposes of closed-loop feedback control?
Let's see. For the first flight we did in science, we had no model. That's one of the great things about insect-sized robots, is sometimes it's actually easier to dispense with the model because, first of all, measuring parameters on an insect-sized robot tend to be very difficult to do. It's hard to get. Nobody sells sensors that are measuring whatever this force is at the frequency you need, that sort of thing. So we relied on adaptive control techniques to compensate for uncertainties in the manufacturing, actually. And that's been a principle that maybe the program managers don't like that much because they want things that they want models and things like that. But for us, like, very often it's proven to be the case that models aren't really, like, we make a model and it just doesn't match the data at all. And there's like 10 parameters and none of which we can really measure, and so we just don't know why that doesn't match the data. And if we want to build a robot, maybe you just make the robot work instead of dealing with the model. There are models for unsteady airflow, quasi-steady models that just measure the drag and the lift, and they do okay, I think. What else? Yeah, so we're playing around with that a little bit, but the models I have don't match the data very well. At least so far. They're off by a factor of 5 or something in lift prediction. So I don't know what's going on. But good question. Yeah, so we don't use much modeling, actually. And yeah. Good question. Yeah.
How effective would sunlight be compared to laser light? Then the issue of targeting the laser on the photovoltaic cell will be removed.
Yeah, great question about sunlight. Yeah, sunlight I think is a possible source of energy. yeah, and it's a nice, strong source of energy. I think that's something we're very interested in doing, is getting sun powered flight. Yeah. So yeah, that's on the short list. Yeah, sun is nice because it's everywhere as long as you are okay with doing tasks that are in the daytime, which a lot of tasks of interest are. Like you can find chemical plumes at night or the day, and day is just the same. What else? Yeah, agriculture. Probably want to do it in the daytime. Look for disease and things. Fires, definitely daytime is a daytime thing. Fires tend to happen where it's sunny, so yeah, good question. Yeah.
Have you also measured how much power you need to fly? Also estimated the energy density of the battery to fly enough?
So the question is power used for flight.
Yes.
A recent, slightly larger version of the fly that I haven't shown here carried. Let's see. I remember the number for this one. So the fly of this design uses about 60 milliwatts to fly all by itself without any sensors on board. So it's going to use more power as soon as you add batteries and sensors on board. And that's assuming you can actually recover some of the power from the piezos using an extra coil, and that assumes we're not recovering any of the power. And that gives you another maybe 20 or 30% better efficiency at the expense of a little bit heavier of a circuit because you have one more coil. As for battery, we don't know what sort of, I mean, there's a very, let's see, there's not much data yet on batteries this small because not many people have made them yet. I haven't looked at, so Rob Wood, they published a paper recently where they came up with a battery, a lithium-ion battery. I haven't looked at the density yet in it to determine how long that would be able to run. So I don't know the flight time there. But yeah, there are other batteries that are small enough, but they're just very low, like hearing aid batteries. I don't know if I mentioned that here, but hearing aid batteries, they make them small enough, but they're generally zinc air chemistry, which is not known for high discharge rates. And what we want is something that will discharge at a very high rate, 60 C, something like that, which is discharged fully in a minute, which you need a very special kind of lithium battery to do that. And very interested in finding collaborators who are interested in thinking about batteries for this kind of application. But that's, yeah, open problem.
Would you like to maybe using wireless power, using, say, like millimeter wave? Perhaps even using like off-the-shelf 5G antennas, which are pretty small.
So yeah, you were suggesting, okay, there's a few companies that are exploring high frequency power sources like that. I don't know. Yeah, that's a good question. Like 5G, these super short wavelength. It may be that those are going to start permeating the atmosphere, and those might be a better source of power. Actually, I haven't looked at that. That's a good point, actually.
Well, I mean, at least you won't have to deal with alignment issues as much as your laser beam.
And oh yeah. So the laser is great, but it's probably the easiest thing to do for us now. But yeah, if you want to have many robots, laser is going to be challenging, and you need to have line of sight, which limits some of what you can do. So yeah, I think yeah, that's interesting. 5G has a much shorter wavelength, so you might be able to use much smaller antennas and capture it more efficiently than longer wavelength. Television is a much longer wavelength, a couple meters or something like that, but it goes through buildings. Yeah, it's an interesting question. 5G. Yeah, I haven't thought about that. Great question. There's another question. Oh.
You showed the plume implementation of Melanie using the moth antenna. Mm-hmm. And you said you used on the Crazy Fly ROS implementation for. What are some lessons learned if you had multiples of these?
So what he's mentioning is that that fly, the Crazy Fly, sends data through ROS to the laptop computer. That's why you can see it plotted on the laptop computer screen there over Wi-Fi. The reason to do that is because it's much easier to do kind of the characterization of the plume and the signal processing on those pulses on the laptop computer in Python just while you're developing it, rather than writing those in firmware on the tiny microcontroller on the Crazy Fly. That said, there's nothing fundamental for why we couldn't do all the signal processing and all the control on the Crazy Fly. It's just it's the sort of thing that I don't think would prove anything, but we're probably going to need to do it at some point just to be very satisfactorily, totally self-contained.
So we are out of time, but let's thank our speaker.